0.053, and that's why this is kind of a unitless concept. And so if we do that, we can say, how long will it take the population to double? So in other words, we're asking, if we start off at t equal to 0, and we start off at size c, so the population is CE 0.53 to the t, and we start off at t equal to 0, then after what time will this right-hand quantity become twice c? And so the c's cancel out, and so you're solving this equation, 2 equals e to the 0.53t. And if we take logs on both sides, we get 0.53t is equal to the log of 2, which means that t is equal to the log of 2 divided by 0.53, which is approximately 1.31. So it means that the population will double every 1.31 units of time. So if a population is growing exponentially at a certain rate, then I can say, when will it be double its size? And this is something that's interesting. So now we come to this thing that we talked about before, and that's super exponential growth. And I can make this a little bigger. It's okay. So this is our best estimate of the world population that started out at time t equal to 0. That's 0 in the AD clock. And by year 1000, it was at that level. So it was the first millennium. And this is the best estimate of the populations, like in 1300, 1500, and so on. Obviously, we've got better estimates more recently. And this is what it looks like. And the question is this exponential growth? And so what you can show is that it's not exponential growth. And the best exponential model will look something like this. And if you look in the textbook, you'll see some graphs of the best exponential model, the best linear model. And this is what we call super exponential. And super exponential growth comes from an equation like this, where we say dn dt is equal to some initial value. And instead of having n here, we've got n to the power 2.144. So if you take this model, it's not growing exponentially, and it's not even growing in proportion to n squared, but something greater than n squared. So that means there's a lot of stuff going on. And so it kind of takes off at this point. And if we look at recent history, we can say, at the turn of the 20th century, what happened? So here we are this is 1800, here's the start of the 20th century in 1900, and up to that point, exponential might be actually fairly reasonable, and then all of a sudden, it shoots off. And so there are various explanations, and some of the most important is the success in eliminating disease. So if you have a look at all the ways you can die, most of it comes from pre-1940s, before the development of antibiotics. Basically, there were all these childhood diseases, some were viral, and viral diseases we weren't really successful in fighting effectively until the start of this century, or towards the end of the last century, when people started developing antiretroviral drugs because of HIV. So that was a big stimulus for antiviral drugs, and in particular antiretroviral drugs. But before that, we had the development of the antibiotics. And so instead of families would have lots of kids and expect a good proportion of those kids to die before they reached adulthood. And then in your adulthood, in the 19th century, you've heard of consumption. Consumption is tuberculosis. And many people would die of tuberculosis. Sanitary conditions were very poor. And so in effectively combating all of that, yet not changing any of our other behavior, still having large families. And then with the advent of technology for producing food, food wasn't limiting in many places. So for example, in Europe and North America and Japan, we're very successful in growing food. And now this applies to Africa, India, and China as well, although starvation is still relatively high, but nothing like it used to be. And so it's taken off. And the only thing that is going to stop this is our behavior, which is already being seen to impact populations in Europe, where in some countries, like Italy, they're actually negative growth rates. So the population is getting smaller. And the only way to maintain those populations is through allowing immigrants in. And you're getting these situations where you're getting an aging population. So there's a real problem in Japan where people are successful in living a long time, and yet they've kept families small. So you have a look at the number of individuals working, supporting the number of individuals not working. And that ratio is changing dramatically in many countries. And it's a big problem for China, for example, that had a one-child policy for a while and still has a fairly strict growth policy. And you're getting an aging population. And so in 30 years from now, China's going to have a lot of old people and relatively few young people. And the only way to solve this problem is to redistribute the young people from places in Africa and India and other places where the population is still growing. Because you can't have a population that's out of balance in terms of the number of people who are not working compared to the number of people who are working. Although we're quite successful in keeping a high lifestyle now with a small work week. And if some of the CEOs of companies like Google, Page, and so on have said we should go to 3-day work weeks. Yeah? Well, that means we started out with 0.159 individuals at time 0 in order to get this to fit. Now, of course, that's nonsense. But so if we're going back, what is the best starting point? So when we do the regression, oh, okay. When you do the regression, you're just fitting two numbers. And it says that if we fit into these points from 1,000, 1,200, so that's the data. We haven't got an N0. This is the best N0. So if we started out with an N0 that was double this, we would miss this quite a bit. And we would have to have a different value there. That's a game. It's a game. But what's important is that over here, that if we fit this model and we say, okay, we don't apply this, we only apply this model from 1,000 onwards, in which case this doesn't mean much. We just calculate our solution, and if we have a look at the solution, so how do we solve this? We integrate. And you can go through this integration, and when you go through this integration, what it says is that you get a solution that so this is what the solution is going to look like as a function of time. And you can put in different values for t. But if you go through here, you'll say, when is when is this term in here? 0, because when this is 0, because it's to a negative number, it's actually an inverse, and the value of t that makes this 0 will make n equal to infinity. And so if you do the integration, you get a solution. So it's a formal mathematical problem, like we did before. But you find out that in the year 250, if you put 250 in this equation over here, you'll get this. So this will be 0 to the power minus 1 over 1.144. That's a negative number, so it's 1 over the inverse of that to a positive number, but that's infinitely large. So that is, this value of n is actually this equation that allows you to draw this blue line. And what it's saying is that this blue line goes to infinity at the year 2050. So when you go through this, it says the population will explode at 2050. Now, obviously, long before 2050, the population, something's going to happen. And that is, there's just not going to be enough food for an infinite number. Okay, so this is solving the equation analytically. Now, equations can only be solved if we can integrate these functions as a function of n. So you see here, when we go through the process of solving this, we're integrating on this side a function of n, and this side we've got a constant times t, and then we do the integration, and we solve for the constant at time 0, and that gives us where we start out at, and we can solve, we can express n as a function of time. So we've got an analytical solution. But now, analytical solutions are only possible if you can integrate the equation. Most equations you can't integrate analytically, and so you have to do it numerically. So for example, here we consider a numerical solution of this differential equation. dx dt is a function of x. And what happens if you can't integrate that function? Well, you can try and integrate it, and if you go through the process of trying to integrate it, you'll get x at t primed is equal to x0 plus this integral. Now this integral, we may not be able to solve analytically. However, we can solve it numerically by approximating derivatives. And so the method that you use, there is a general method, and in calculus textbooks, people are interested in functions where the right-hand side is not only a function of time, of x, but it's a function of time as well. So how can that be a function of time? So let's come back to this equation. What would happen if my per capita rate of change changed over time? This is d as a function of time. Then I would get r as a function of time. And so my right-hand side would be a function of both x and a function of time. Now, is it possible that it can change with time? So if this was a model of how a population is growing, we've seen that in a human populations are not just growing at a constant rate. To get the super exponential rate, they had to actually grow at faster than a rate that's proportional to x. And there we saw that what we changed was it's dependent on x to be dependent on x to some power. But it's also possible that r is not constant. So, for example, imagine you had a yeast population, and the yeast population is growing, but because of mutations, at a particular time, it turns out that one of the cells mutates and grows faster. Then you have individuals in that population, some growing faster, some growing slower. So this is actually changing over time. Or if you've got a population, like a human population growing exponentially, and individuals start to alter their behavior because they say the population is growing too fast, you can slow things down by changing the growth rate. And this would happen in many countries, is that the number of kids, the birth rate went down, the death rate also went down, but the birth rate went down much faster than the death rate. So you can get these as a function of time. Now again, if you want to read the chapter on differential equations in the textbook, you can, and you can read this. But ultimately, a numerical method is you start off at a particular point, and then you calculate where the next point will be for a certain time interval h. In NOVA, that time interval h is called delta. And you can see that if you take a big step and you use a linear approximation, that if the population is growing faster than linear, and you use a linear approximation, you'll only get to a point that underestimates where you should be. And the bigger h is, the more you will underestimate where you should be. So in other words, if you want to be accurate, you need to start to take a small value of h. And you need to use a formula like this. This formula is a difference equation. So you take your differential equation and you turn it into a difference equation, and you don't calculate. When you do something analytically and you integrate, you're integrating over time steps that have gone to 0, because that's what calculus does for you. It gives you a formula, takes a sum and turns it into an integral. Here you just work with the sums and the finite steps that you take to calculate where the next point is. So again, you don't need to do this for this class. Those of you who are interested can read that. Some of you who've taken calculus may have seen this vector field method for solving differential equations. Who's seen that? Okay. But what the computer does is it takes a differential equation and turns it into an approximate difference equation where you calculate your next value from your previous value plus the length of your interval h times evaluating your function at the previous time step, which is the same as saying I evaluate the function here, and then I just go out linearly along a line to calculate where the next point is. And you can see that if the solution is changing at a rate that's faster than linear as in exponential growth, you'll underestimate what's going on. And this is called the Euler approximation. Now, whenever you solve something numerically, you need to use the Runge-Kutta approximation. The Runge-Kutta approximation doesn't use this formula, but uses a more complicated formula, and hence gives you better estimates of what's going on. And I don't know how many of you picked up on this, but what I said is, how do you know what value to choose for h, or in this case, something that we call delta in the NOVA model? So you can start off with delta equal to 0.1 and you get a solution. You can compare that to a solution with delta equal to 0.2. If the solution doesn't change in the first 2 or 3 decimal places, and you say that's accurate enough for me, then you're done. However, if the solution changes, let's say in the second decimal point, or the second significant figure, and you want greater accuracy than that, then you'll choose delta equal to half of 0.1, which is 0.05. And then you'll check the difference between this solution and the solution at 0.1. If it's still not accurate enough for you, in other words, if you want it accurate to 2 significant digits, but if you compare the solution, they differ in the second significant digit, then you can make this equal to 0.025, and you can keep halving it until you get the solution you want. Okay, so that's more or less for today. We were going to talk about the logistic if we got time, but we're going to do that in a couple of weeks, because the logistic equation, and we'll come back to the Carlson's data, but if you take Carlson's yeast data and you plot it further than we plotted it over here, you'll see that he actually gets a set of data that's fit very nicely by a logistic equation. And in the yeast data, what the population is running out of is space to grow.